This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
And relative permittivity, and we'll go through that. There is something called the loss tangent. It's okay, I'll go through all the lectures here. You don't have to write this down, right? I'm just giving you a prelude to the lecture. And that's important in dielectric materials. And then what we'll do is we'll talk about, things like skin depth. Okay, so let's start. So whenever you apply an electric field to a dielectric, what happens is that you get those rearrangement of charges in that actual material. Okay? Now, if it's for example, a piece of glass, right, which is a silicon dioxide, which is a standard dielectric material that's used in chip design. Like, for example, when you're talking, a lot of you have been talking about MOSFETs. Usually, the assumption is that the oxide's silicon dioxide. Now, in order to increase that dielectric constant of that material, people are beginning to go to hafnium oxide and things like that, which have high dielectric constants but also lower leakage currents. But here, so suppose you've got a material, you apply an electric charge, you apply a field across it, you actually get redistribution of charges within that material. And what you're able to show is that the displacement flux delta, which was, remember, div of delta equals to the total charge, or that is equal to the total charge, and that was one of Maxwell's, or Gauss's equation, which is one of Maxwell's equations. You can rewrite this as the displacement vector is equal to epsilon naught, which is the permittivity of free space, and multiplied by the electric field, plus a polarization component. Right? Now, and that polarization component is supposed to account for what? Can anyone take a guess? The redistribution of charge because of the electric field, right? And in a linear medium, what you can actually show is that its polarization component is equal to epsilon naught times something called the electric susceptibility by the electric field. Now, rewriting this equation in terms of just the electric field, what we can actually show is that E naught plus 1 plus psi E is equal to epsilon, and then what we do is we write it in terms of a real and imaginary component. Right? There's no magic here. It's just, I've just said, hey, we're writing down the dielectric, the permittivity of this particular material, and for argument's sake, right, a bit of hand waving and just saying, due to, because of, the best way of describing it is because of a bit of hand waving, I've said, well, I can rewrite that as something which has a real component and an imaginary component. And the reason why it's been done specifically like this is, as you'll see later, is that in a material, once you apply an electric field, as part of that polarization process, and it's polarization depolarization if you've got an AC field, you polarize and you move the charges in a particular way, but there's also energy that is lost as part of that component or part of that process. And that's where that J epsilon, the imaginary component, or what the imaginary component is trying to capture. Right? Now, I've talked about a material such as glass, and the relative permittivity of glass, I've said, is roughly 4, or silicon dioxide. Does anyone know, or can anyone tell me what they if they know what the relative permittivity of seawater is, or just water. Would it be a small number? Would it be a large number? And why? Okay, it's a large number, right? So, and it's important because a lot of times when you're when you go through this process, what you'll find is water, and that's, yeah, the dielectric constant of water is quite large. If it's salty, it's also quite lossy, and that's why you cannot communicate with radio waves or high frequency radio waves through, how do you call it, through the ocean, right? But the reason is, can anyone tell me about H2O, the molecule H2O? It's a polar molecule, right? And if you apply an electric field, what do you think is going to happen? The magnetic field. Oh, sorry, electric field. Right. And because it's able to do that relatively easily, because it's a fluid rather than a crystal, like for example silicon dioxide, where the protons or the atoms or the nuclei of the atoms are tightly fixed. There you can only play around with the electrons and try to pull them away, but you can only pull so many away before the charge of that nucleus becomes large, and that's why crystals in most cases don't have as high dielectric constant as certain fluids, right? And especially polar fluids. Anyway, so if we continue on with this, we also know that any material has conductivity, right? And we can always write the current. This is essentially Kirchhoff's or Ohm's law, I should say, in Maxwell's form, which is the current density equals the conductivity times the electric field, right? So you can actually rewrite that as just Ohm's law. So if we substitute what we've just described, which is, this is just, everyone remembers this, right? This is just Maxwell's, the extension of Ampere's law, right? But I've written it in phasor form. What does that mean? Does anyone know what having something in phasor form means? I've just assumed that the signal that I'm exciting the system with is a sinusoid, right? And then essentially, wherever I've got a time derivative, I just replace it with omega times the quantity that I was interested in, right? That's all I've done. And then what I've done is I've said, well, we know that the displacement, the displacement flux for this material is just E, electric field, and we know that the current is the conductivity plus electric field. And if I rewrite this, the curl of H, I can get the curl of H is J omega, epsilon single dash J epsilon double dash minus J sigma on omega. Oh, yes. Thank you. This is a problem. I apologize. Okay. All right. So, if we look at this, what can we say? Well, we've got two components. We've got the epsilon component, and then we've got the imaginary component. And what we said was that the imaginary component was the loss component. And the other thing is that the loss in the dielectric is indistinguishable, because it's, again, it's an imaginary component, so you've got E epsilon double dash minus sigma omega double dash, and they're both imaginary. So you've got the loss in the dielectric is indistinguishable from the loss in the conductor itself. Now, usually, so other than some boring mathematics, Stan, why did you waste our time? Why are you telling us all this BS, right? is probably the question you're all asking. Now, if you're looking at a material data sheet, usually they define a quantity called the loss tangent. Okay? Now, can anyone tell me why would they define the loss tangent? Okay, so who's designed the PCB board here? Okay. Anyone else? Yes, no? Yeah? Okay. So what material did you use? The people back, what material did you use when you designed your PCB board?
For the board itself?
Yeah.
Oh, I don't know.
So if I said to you, I wanted this board to work at 10 gigahertz, what would you say to me? Sorry, if I asked you, does your board, I want it to work at 10 gigahertz. And would you say, well, I think it will work, or maybe not, or so how would you be able to look at a material data sheet and say, Stan, guess what, you're dreaming. This board, this material ain't going to work. So what two things do the data sheet, does the data sheet usually tell you? It tells you multiple things, but related to the propagation of radio waves and signals on that PCB board. You know? Yeah, go.
The material you usually use for masters level stuff is FR4.
Right. So, yeah.
You probably use brushes for something that...
I try to use, I still try to use FR4 because it costs me 4 cents per square inch, whereas Rogers cost me $1 per square inch. But when you look at it, what usually they give you in the data sheets is they give you the dielectric constant, which we'll find out why that's relevant, right? Including working out what an impedance or how to make matched impedance lines on that PCB. But they also define for you or tell you what the loss tangent is. And essentially what that does is it allows you to work out the ratio of the signal that is actually propagating versus what you're actually losing, right? So therefore it indicates to you or provides you with the information so that you can actually know what your loss is per millimeter of track length, right? Because when you're making tracks on a PCB board, if they're slow, you don't really care because the loss isn't quite large. But if you start going up to 10 gigahertz or 60 gigahertz, all of a sudden you might be getting 3 to 5 dB of loss per millimeter, right? So all of a sudden, if you've got a large board and you want to go across it, all of a sudden you might be losing 10, 20 dB. And that's why you want to know the loss tangent at a particular frequency. Right. So that's the reason why I'm telling you this. So therefore, it's not that I just want to torture you. There's a reason, right? So therefore, what you do is you find you have the loss tangent, and essentially, depending on the material, and you've got the relative permittivity, you can also work out what the complex permittivity of for that material is for a specific frequency. Okay, so that's where it becomes. Why it becomes useful and something that you need to know these relationships, because it actually tells you what the loss tangent is specifically providing to you, and through the techniques that we've used in order to derive it, is what is your loss through that material. Okay, and we're going to use this also in the next towards the end of the lecture in order to work out why sometimes we coat certain materials with metals in order to use them as I was going to use it's not isolators, geez, I'm drawing a blank, to stop the conduction into that material, just like a Faraday cage, sorry. And that's part of the thing that we'll also discuss. Okay, now the question. So this is a question for everyone, right? I've written the displacement flux is epsilon in this particular case a scalar, times the electric field. Is this relationship always true? Well, the way that I've set it up, the answer is it must be no, right? I mean, I've set it up so that you can actually easily just say no. When is it not true? Okay. Has anyone heard of anisotropic, I apologise, I'm probably not saying that correctly, materials? Which means that the capacitance in one direction is not the same as the capacitance in a different direction. Like, for example, there's certain crystals, right? And what you'll find is with certain crystals that depending on the axis of that crystal, depending on the direction that you apply electric field, you get different dielectric constants, right? And one of the prime examples of that is a material called lithium niobate, which you actually use for lots of things, including in optical communications, but you also use it when you're trying to sense electric fields, right? So you can actually use it, if the electric field is slowish, you can actually do some tricks where you can actually view the electric field. And we're talking about, when I talk about gigahertz, when I talk about slow, I usually mean a few gigahertz, right? And you can actually see it. You can actually capture it and see it. Anyway, so the answer is this doesn't always hold, right? And an epsilon in most cases, including crystal structures and ionized gases, are anisotropic, right? Now, I'm probably getting a bit ahead of myself in this particular case, but usually I love talking about this kind of stuff, as you can tell. So there's one of the things that you probably won't do, we will definitely not do in this course, but you might see it sometime, as being engineers, is that you can actually start making antennas out of plasmas. Does anyone know what a plasma is? No? Have you, an ionized gas, right? So you can actually build a very interesting antenna out of a plasma, an ionized gas. So therefore, if you perturb it, you can think of it as a current. It's also got a dielectric constant. You give it a kick, an electric kick, begins to oscillate. You can actually radiate. If you want to be able to turn it off so that people can't see you, not necessarily the light, but I can't actually see the reflection from that antenna or the radiation of the antenna, you can switch off the ionization. So you can start playing some really interesting tricks, which you might come across when you're doing some, if any of you decide to do a PhD or research in this area. Now, of course, the same, and I won't derive all this because you'll just get bored, the same process applies for magnetic fields, right? So therefore, it's not only anisotropic, not only are there anisotropic electric materials, there are also anisotropic magnetic materials. And there's a lot of interesting work that's currently being undertaken in building very interesting materials or metamaterials using, various types of nanoparticles, including ferric oxide and the like. All right, cool. All right, so now let's go through and talk about what happens when materials or fields hit a material. What happens at that interface? Right? Wow, who bought all these Tim Tams? Anyway, sorry, I just saw all these Tim Tams out. And this is important, right? And the reason why I've put this in the lecture notes is if you want to do shielding, it's all about knowing what happens at these material interfaces, but also whenever you have some kind of wave hitting a dielectric material, you also have some of the energy that goes through, some of it gets reflected. It's a case of understanding what actually happens at these interfaces. And here what I've done is I've drawn an arbitrary material interface, and I've said material 2's got a permittivity of E2, permeability of mu2, medium 1's got a permittivity of E1 and a permeability of mu1. And I've drawn on this arbitrary surface the tangential tangential and normal electric field components, and I've also drawn the sorry, I should have put this as a B or a H. Sorry. Yeah, and tangential and normal magnetic field components. So, in order to understand and be able to apply Maxwell's equations, because Maxwell's equations are, some deities, or if you want to say God's gift to electrical engineers, so that essentially describes, or is the machinery that we have available to us in order to understand and predict and determine what's actually happening at a surface. So the way that we do this, and you've probably seen this in your first year physics, where the argument was you've got an arbitrary shape. They would call it a little, they would ask you to draw a little pillow box at the surface, which is essentially a cylinder, and would say, well, this cylinder's got a top surface, and it's got a surface, the surface surrounding around the circumference. And what they would say is, well, tell us what happens, or determine what happens in the limit of that particular cylinder's, when the height of this particular cylinder goes to 0, right? And that's essentially what you do in order to determine what's happening with the electric and magnetic fields at this particular interface. So, if you apply Gauss's law, right, and here I've written it in integral form rather than differential form, and you have h approaches to 0, what you quickly realize is the difference in the normal components, right, because all the contribution on the side has tended to 0 because it's become, I've taken the limit as the height becomes 0, and I've only got the the top and the bottom components of this cylinder, and you can actually see that you essentially have to have continuity in the displacement flux, and essentially the difference between the flux between the two materials is equal to the amount of charge that is actually accumulated at that surface. Oops. So and colloquially I'm using the word guys, if I'm not, if you can't see what I'm talking about, just say, Stan, move it up. Because it's hard, when I'm looking at it, I can actually see it, right? So, and also all the lecture notes for the next few lectures are online, right? So you can actually download them also. Now, if we continue our analysis, right, and we go, we know that there are no magnetic monopoles, so we also know that the magnetic field is continuous. So therefore, we know that the magnetic field cutting any of the surface, the field coming in has to equal to the field coming out. So we've got B2 equals B1. And likewise, if we use Faraday's law in phasor form, what we can do is we can actually show that what this implies is, the difference in the normal of the electric field, the tangential, sorry, in this particular case, the normal or the tangential component of the electric field also has to be continuous. And from the Maxwell-Ampere relationships, we also know that the magnetic field, the difference in the magnetic field is equal to the current that's actually flowing on the surface. Now, what does this all mean, right? So, why did I waste everyone's time again? Well, depending on where we're at, or what the interfaces are, there are those relationships are slightly different. So two of the most important interfaces that we encounter is free space onto a dielectric interface, and on those and under those circumstances, there's no charge or surface on that current or surface current on that particular surface. And what you can see is the displacement currents, the displacement fluxes, I should say, the displacement of the magnetic fields, the electric field, and the tangential. And the magnetic fields are all continuous across this surface. Where it gets interesting is when we've got a perfect conductor. Now, mind you, a perfect conductor doesn't exist, but for all intensive purposes, if we're talking about certain materials like copper, gold, silver, which have very, large conductivities, what we know, and we use this as, when we're trying to build, shielding, that the fields inside these materials goes to zero, and if we follow through the same arguments, what we can actually show is, again, the charge that accumulates on the surface is related to the imposed field, that the normal magnetic field tends to zero, that the normal of the electric field also tends to zero, and then also the normal of the magnetic field is equal to the amount of current that flows on the surface in order to cancel the field that's being imposed. Now, there's an important consequence here when I've said a perfect conductor. Suppose I had, and this is because I always see it all the time. People, after you get a new employee, and you ask them to do some experiment, and it's noisy, and you say to them, didn't you shield your experiment? And they go, yeah, I put a metal box around it. You say, well, did you? So why is it noisy? Can anyone? I was about to give you the answer, but I didn't. Luckily, I didn't, so I can ask it as a question. Why can I not just put a metal box around something and assume that that's going to be a perfect shield? Okay, so if I look at these equations, right, so the first and the fourth, so if I go, I'll just label them 2, 3. So if I look at the first and the fourth, what's the assumption? Yes?
That we have a perfect conductor.
Sorry?
That we have a perfect conductor.
We've got a perfect conductor, right, which means that there's an infinite amount of what? Charge which can flow, right? If you've got a normal conductor which is ungrounded, you can't, after a while, you will set up enough, there will be enough, that material won't have enough electrons, or, not that it won't have enough electrons, that's probably not the right way of describing it, that it can't suck enough electrons to where it needs to put them in order to cancel out the fields. So that's why you need to ground that box. If that box is not grounded, it ain't going to be a shield, right? So, during your first job, when you're asked, hey, make some very sensitive experiments for me, or undertake some very sensitive experiments for me in order to work out the sensitivity of this new great chipset or new phone that you've produced, make sure that the shield, or which is the Faraday cage that you produce, is actually appropriately grounded. So yes, you need it to be a conductor. If it's a dielectric, it won't work to begin with, no matter how you ground it. But if it's how do you call it, a conductor, make sure that it's grounded, so therefore you can actually get some level of shielding. Okay, so let's move on. Okay, so the next thing I want to do is talk about the propagation of these waves, or plane waves, in both source-free, linear, and isotropic and homogeneous regions. So essentially what I've done is, again, I've taken the the two Maxwell's equations, and because I'm in a source-free linear isotropic region, what's happened here is I've dropped the j omega component here, right? Because current can't actually flow. And then what I do is I use the following property of vector fields. Oops, good, thank you. Of vector fields, and what we do is we come up with essentially this equation, which is essentially the Helmholtz equation. So if you go through this and you go through the mathematics, you have, you know, the gradient squared of the electric field plus omega squared mu e epsilon e equals 0, right? And likewise you have the same for the magnetic field. Now, once you go through and you try to solve this, especially if it's in one dimension, as we're talking about here, you can rewrite, you know, here all I've done is k squared is just omega square root of mu epsilon, right, which is, I've just replaced that with k squared, I've called that k squared, and, you know, solved this three-dimensional differential equation. I've said, look, I'm just going to be interested in a plane wave traveling along the z-axis. And that's informative enough for what I'm trying to do here, right? So I don't have to solve the arbitrary three-dimensional propagation equation. And what happens is, when you solve this equation, like you find in transmission lines, and we'll find in transmission lines, is that you have a forward-moving electric field and a reverse-moving electric field. Right, one's going in one direction, one's coming in the other. Okay, and here what I've done is I've just said, well, let's rewrite that as cosines. I mean, this, I could have chosen sines, I could have chosen e to the minus jkz, whatever. All I've done here is actually included the time component into this equation. Now, and the reason why I've done this is to be able to then work out the velocity of a wave, right? So what I want you to be able to figure out is the velocity of the wave, which is essentially just the z dt. And if you go through, you know, in the mathematics, it's quite simple. You go omega t minus c on k, you differentiate with respect to t, you get omega on k, which is just 1 on the square root of mu epsilon, right? So that's actually telling you the phase velocity, and it's also useful because it also tells you not only the wavelength, it tells you the phase velocity. All right. What does the phase velocity mean? Has anyone heard of the phrase phase velocity? Can anyone tell me the difference between, I'm sure you've done this in physics, right? So, you know, come on, give me answers. You've done phase velocity and you've done group velocity, right? Yes? Yes or no? Who has not heard of phase velocity? Okay, one. Okay, so everyone knows about phase velocity, right? What does phase velocity mean? For the people that didn't put up their hands, what does phase velocity mean? Yes?
It's the velocity of the front of the wave.
Right, in that particular medium. Yes. Okay, and that differs from group velocity how? Yes?
Group velocity would be the velocity of the information that's being transmitted.
Correct. So it's the transfer of momentum. How fast can you transfer momentum? All right? So you've done it and you just don't want to play games with me, or you just think, you know, we do know or something? I'm just curious. Everyone's looking down. Come on, guys. It's supposed to be a backwards and forwards, right? You're supposed to be, Stan, no, we know this, Stan. You're wasting our time. We've heard it a million times. Stan, is this going to be on the exam? You know, at least something. No? All right. So, suppose I had... All right, can someone tell me what they think the speed of light... of a electromagnetic wave in salt water, or in salt water is going to be, or in water. Water, salt, just water. Would it be higher, faster, or slower than in air? Who said faster? Someone said faster, so it's slower, right? How much slower? So the relative permittivity of water is around 80, right? So therefore, and the permeability of water is 1, right? Because it's not a magnetic material. So how much slower would it be? Guys, the equation's here in front of you, right? All right, so therefore what it will be, if you're in a different material, it would be the speed of light. So I'll just write this, which will be 3 times 10 to the 8 on mu remains the same, right? So mu r, you can write it mu r e r. So we'll write it 1 times the square root of 80, which is, say, 9. So, and roughly 10. Let me approximate that by 10, right? So therefore, it's 3 times 10 to the 7 meters per second. Right? So it's 1/10 the speed, right? So don't, please, if you're reading these lectures, don't come back to me and say, well, Stan, you've done square root of 80. How did you get from square root of 80 to 10? It's just an approximation, right? Now, we know, what do we know about a wave? If we wanted to work out the wavelength of the material, what do we know? Okay, why do we care about the wave? Why do I care about working out the wavelength of at a particular frequency in the material?
It will influence the velocity of the electrons.
No, not really. It's not that, right? Okay, for the people that have designed PCB boards, right? And you've designed an inductor, or you've designed a capacitor, or you've designed an antenna on that material. Yep.
If the wavelength is on the same scale than the side of the circuit, then you can have an effect on the circuit as well.
So what you do is essentially all the passive components, like the inductors and all that, scale with wavelength, right? So if you're building a transmission line and you want, for example, a quarter wavelength transformer, right? And we'll go through this in greater detail. What it means is if the material has a higher dielectric constant, it means all those components will be smaller, right? For example, if you had a material, for example, if you were doing something at 2.4 gig, which the wavelength, if I'm doing it correctly, is about 12 centimeters, right? If you wanted half a wavelength on a PCB board, all of a sudden that's 6 centimeters. That's significant, right? But if you decided to make it an FR4, which has got a relative permittivity of roughly, I think it's about 3.5, 3.6. Let's, for argument's sake, I can't do the maths in my head, say it's 4. Square root of 4 is 2. All of a sudden, if I wanted half a wavelength, I'm now at 6 centimeters, right? Then I can play another trick. I can say, well, maybe that's still not good enough because I've got to put it into a mini PCI slot into my computer or my laptop or my colleague's iPad here, and I want to make it even smaller. Guess what? I will use a higher dielectric material. Maybe I'll use a ceramic. And if the ceramic's got a relative permittivity of 10 or 12, all of a sudden it makes everything even smaller. Right? That's why you need to know, because it affects all the analog components that you build on PCB boards. That's why I'm telling you about all of this, right? Okay, so what it allows you to do is, we've got a wavelength in a medium. We know that the wavelength of the medium, we know, the relationship C equals FL, right? Especially for that's the relationship which determines the frequency and the wavelength. So the speed in a material is frequency times wavelength. And what you're able to do is to say, well, you can rearrange that. We know that the speed's now gone mu on r naught, which also tells us what the wavelength is. So essentially, all we're saying is, if you're in a material which has a certain relative permittivity and relative permeability, that actually decreases your wavelength. All right, and that's very important when you're designing passive components on PCBs or other types of structures. Now, if we continue from here, what we know is, again, back to Maxwell's equations. If we go through this whole process again, what we're able to do is we can now relate electric field to magnetic field in air or any other material, and the relationship between the electric field and magnetic field, this 1 on eta, is referred to as the wave impedance. So if I said to you, if you had an exam question or you were designing, if someone gave you the characteristics of an antenna in its far field, and I have to emphasize in its far field, this relationship doesn't hold in the near field, and we'll go through this in the next few lectures. What you can say to me is, Stan, if I know the electric field, in the electric far field, I can tell you what the magnetic field is, right? So that's what I'm deriving here. So I'm actually telling you, depending on the material, if you know the wave impedance, which is the material, and you've got the electric field, you can say what. If I give you the electric field, you can tell me the magnetic field, and if I give you the magnetic field, you can always give me the electric field. Right, and that relationship is related to the wave impedance, and the wave impedance of free space is 377 ohms. Now, if we now look at in the previous slides, what I've done is I've talked about plane waves in vacuum, right? Now, what I'm going to do is consider plane waves in a general lossy material. All I'm doing here is just going through the mathematics again, and also including that there's this complex permittivity, and then also there's conductivity in this arbitrary material. If I rewrite Helmholtz equation in terms of these other quantities, what happens is I had this following equation to solve as compared to this equation, right? So you can actually see that there is now some other components in there, which is, and remember K is the wave number. So here what we've got is, and K relates to the propagation constant. So if we go through the mathematics again, what we can do is we can rewrite this propagation constant. We can determine what the propagation constant is in terms of these materials, of the property of these materials, specifically permittivity, permeability, and conductivity. Now, what we say is, and this is arbitrary, right? This holds for any type of material. Now, what I'll say is, let's assume that it's an arbitrary dielectric. What we're able to do is, we know for a dielectric that the conductivity is exactly equal to 0, and what we can do is rewrite the propagation constant as j omega square root of mu e, and we can also rewrite this in terms of relative permittivity and the loss tangent, right? And in this particular case, that the loss tangent is actually telling us how much how fast that signal decays in that medium.
Excuse me?
Yes.
What is epsilon dash compared to epsilon?
Epsilon. Okay, so remember we had epsilon was, I said epsilon is an arbitrary complex number, and epsilon dash was the real component minus j epsilon double dash, which was the imaginary component. Okay, so that's slide number 8. Now, what happens if we're in a good conductor? Okay, we can go through the whole process again and work out what the propagation constant is. And what do we know about a good conductor? Essentially, all I'm doing here for a good conductor is saying that S is very large, right? That's all I'm doing. And I'm forgetting about, and if S is very large, sigma is very large, what I can do is I can forget the 1 minus whatever, I can forget the 1, and I've got minus J, right? And what I can do is, if you remember back to your second year mathematics and de Moivre's theorem and the like, you can rewrite the propagation constant as, you know, once you simplify, as 1 plus J square root of omega mu sigma on 2, right? And we said that the real part of the propagation constant is how fast the wave is travelling. The imaginary component is how fast the signal is decaying. Now, what this does, or what this allows us to do, is now define this concept called skin depth. Who's heard of skin depth before? Yep. Do you want to tell us about skin depth? Not really? I mean, it's okay, but have a go. All right. And I like the interaction, so I prefer for people to say something, you know. No?
Happy to have a go.
Yeah, have a go.
Is it the amount that a wave can propagate through a material before it cancels out or decays?
Right. So essentially, the skin depth is when you've got a wave, how far can it travel into the wave before it decays by e to the minus 1, which is 1 on 2.73. Right. So it's how fast, what depth before you get the single 33% loss of your signal. Right. That's all it is. That's one skin depth. Okay. Now, what we'll do is, hopefully we can see this, and this is in the slide. So what I've done here is I've just written a little table for you. So if you've got a lossless general, lossy, and a good conductor, I've written down the propagation constants for you, the wave number, the attenuation constant, and also the skin depth, right? And I've also written for you the wavelength and the phase velocity. So let's put a little bit of theory into practice, right? So I've got a few more minutes, so let me just go through this. So this is a question, a set of questions, and let's start work these out together. So we've got an electromagnetic wave, and it's traveling in a medium, and it's at 5 gigahertz, right? And usually I love 2.45 and 60 gig numbers because it's, you know, Wi-Fi, and I've been using them for, you know, the last 15 years. And I also tell you that it's an electromagnetic wave, its frequency is 5 gig, and its wavelength is 3 centimeters. What do we know about the speed? Okay, let me take that back. Who can work out what the propagation constant is? Who can remember what the propagation constant of this material is? Sure, it's 2 pi on lambda, which is, you know, if you go 2 pi on lambda, we know that the wavelength is 3 centimeters, so it's 2 pi on 0.03. So it's 209.4 per meter. Okay, how about the phase velocity? All right, who can guess the phase velocity? Okay, what do we know about? Yeah, lambda f, perfect. All right, so it's just 0.03, which is our wavelength. Frequency is 5 gigahertz. So it's telling us that the phase velocity is 1.5 times 10 to the 8 meters per second. Right, so it's half the wavelength, it's half the speed of light. Okay. All right. What's the permittivity? I shouldn't have put that on there. I'll put it on now. Okay. Sorry. What's the permittivity of the medium? Well, we know that the speed is half, right? So therefore, we said 1 on square root of mu r ER of vacuum is the speed in that new medium. And what I should have said is a non-magnetic material, so therefore it's mu r equals 1. So we want to work out ER, the relative permittivity. And once we go through this, you can actually work out the relative permittivity. And the relative permittivity is 4, right? So it's very likely the material I'm talking about is silicon dioxide. Okay. And the last thing I wanted to work out was the wave impedance, right? So we said the wave impedance is what relates electric to magnetic field, right, in the far field, right? And in this particular case, we know, and you can actually derive it, that the wave impedance is the wave impedance in vacuum divided by the square root of the permittivity, and you can derive all that, and it's 188.5 ohms. Okay, excellent. Let's do another example before we sum up, right? I've got another few minutes, is that correct? All right, good. All right, now I'm going to ask you to work out the skin depth of a few materials, right? And specifically aluminium, copper, gold, and silver. And in this particular case, sorry for the, how do you call it, the messy slide. We know the relationship, the skin depth is 2 omega mu on sigma, where omega is 2 pi times the frequency. That's angular frequency. And what we're able to do is we can rewrite just some trivial algebra here. We can rewrite this as, calculate this for that particular for the particular frequency and for these non-magnetic materials, and that turns out to be 5.03 times the square root 1 on the conductivity. Now, if I go through the calculation, right, what we can actually show is, essentially, once we've got the conductivity, we can also work out the skin depth. Now, the skin depth of aluminium is, roughly a micrometer, right? Copper, roughly maybe half a micrometer, right? Now, do you find this surprising? Or do you find this at all useful? Why would this be useful? Yes?
When you're trying to design shields?
Yes. Yeah, you're trying to design shields, or like what I've been doing at 60 gigahertz, right? Suppose you want to build a horn antenna, right? If you're at if you're at low frequencies where your skin depth is large, what it means is you need to get real pieces of metal, cut it, and go to the metal workshop. And for people like me that are electrical engineers, going into a mechanical workshop usually means cut fingers, right? So try to avoid those things. But if you're at 10, 20, 60 gigahertz, one of the things that you can actually do if you want to build a nice waveguide or a horn antenna or something like that, well, go 3D print it. Just electroplate a thin film of gold or copper or chrome on the surface, and you've got a beautiful, immaculate little antenna or waveguide or Wilkinson power divider, right? So all of a sudden, because as you go up in frequency, the skin depth is so small, it means you can just electroplate a little bit of plastic, and you can start making some really cool stuff. Or at least it's cool to me, right? So you can start all the stuff. And I guess what you're maybe not appreciating is that back in the day, if you wanted to buy a waveguide, right, or an antenna, or anything at 60 gig, right? You'd walk into the, you'd buy it online, and for a waveguide, people would say, oh, $15,000 or $25,000. And you'd be like, oh God, what am I going to do? But because the skin depth, because of the advent of 3D printing, and also the skin depth being so, small at those high frequencies,